Thank you so much. It is my pleasure to introduce Francine Schevenhoven. Francine did her, studied mathematics at the University of Utrecht in the Netherlands. And during her master thesis, she was introduced to supermodeling, and she will tell us more about this later. And she liked it so much that she continued to work to it during her PhD. And she worked for a PhD with Noël Kindlyside and Frank Selten from the Netherlands and in Bergen in Norway. She just graduated and started a postdoc at CU together with Greg Dwayne, Noël Kindlyside, Frank Selten, and Jeff Weiss. When I heard about this, luckily she had some administrative problems. And so Frank reached out to me, and so I could help her. And then I said, why don't you give a talk? And that's why this talk was scheduled so at the last minute. Francine will be here for 2 weeks, but then come back throughout her postdoc. And she will be here part of the time in Bergen. Francine will talk about the training of supermodels in the context of weather and climate forecasting. And I'm sure she will explain what supermodels are, because most of us don't know that yet. Welcome, Francine.
Yeah, Judith, thank you very much for the introduction. So for my PhD thesis, I worked on the training of supermodels. And the next, 30 minutes, I will explain to you what training a supermodel means in the context of weather and climate forecasting. So probably you are familiar with the standard multimodal ensemble. So it means that we have a couple of different imperfect models, as you can see here in the figure on the right. And then we integrate them separately, and afterwards we combine the data. And this can be very helpful, for example, to get improved statistics like the mean, because model errors, they tend to average out. So for example, when one model is too warm, the other model is too cold. And also the spread between the models, it can give a measure for uncertainty. But what the multimodal ensemble does not always do is giving an improved trajectory. And that's because the models are not fully correlated. So if you average their trajectories, then you will suffer from variance reduction and smoothing. So we think we can do better by using a supermodel. So in a supermodel, the models interact with each other during the simulation. So as you can see in the figure here on the right, the models, they exchange information with each other, indicated by these arrows. So they're dynamically combined. And what I really like about the supermodel is that you can create new dynamical behavior. So for example, when you have two models that have the same type of error, but for different reasons, then you can resolve this error. Also, you can correct errors at an earlier stage compared to the multimodal ensemble because of this exchange between the models. And the idea is that models are synchronized within a supermodel, so that you don't suffer from this variance reduction or smoothing as in the multimodal ensemble. But because the models are synchronized, you don't suffer from this. So the models, they talk to each other, and together they decide on a common trajectory to follow. So then there are different ways to construct a supermodel. So one of the first was to use an interactive ensemble. So this is an example of a colleague of mine, Maolin Shen. And he had two different atmosphere models with a different convection scheme, the Tietke and the Noordeng scheme. And he combined that to one ocean model. So in this way, both atmospheres, they receive the same sea surface temperature from the ocean. And because of that, you got some synchronization, mainly in the tropics. And on the other hand, the ocean received a weighted average of the fluxes of the atmospheres. And then these weights, they were trained to minimize the errors in the tropical Pacific SST. So then when we look at the results at the climatology, then here you can see the sea surface temperature in red and blue, the precipitation in these black contour lines, and the wind with these blue arrows over here. So I think that many models, they suffer from this cold tongue bias. So that means that here in the tropical Pacific around the equator, the temperature is too low in the models compared to the observations. So you can see it clearly in this Noordeng model. And also many models, they suffer from this double ITCZ, or the double intertropical convergence zone. And that means that here south of the equator, there's more precipitation than in the observations. So you can clearly see that both Noordeng and Tietke suffer from that. But then the supermodel, on the other hand, you can see that we got rid of this cold tongue bias and double ITCZ error. So I think this is already a really nice example of how you can correct the dynamics when you have same type of error in models in a supermodel. But then we got some synchronization in the tropics in the experiment of my colleague. So this is where we got improvement in the results. But in order to get globally better results, we need more synchronization. So not only that the atmospheres are connected through the ocean, but we want to let the atmospheres communicate directly with each other to get more synchronization. So how to establish this connection? So for example, you can work with a connected supermodel. So for example, if we have two imperfect models with parametric error, and as denoting the supermodel solution, then this denotes the evolution equation of the individual models. And then we nudge the models towards each other with this nudging term over here. So this nudges model 1 towards model 2, and here the other way around, model 2 towards model 1. And then the idea is, of course, that we have a lot of synchronization, but there might not be perfect synchronization. So then we define the supermodel tendency as the weighted average of the tendencies of the imperfect models. And then another way to form a supermodel is a weighted supermodel. So that means that, again, we have our evolution equations, and then the supermodel tendency. It's just a weighted superposition of the time derivatives of the imperfect models. And then this supermodel tendency, it's given back to the individual models to continue their run with. So then, of course, the question pops up whether you want to work with a connected or a weighted supermodel. So a connected supermodel, it allows for more flexibility. So for example, when you let the connection coefficients vary in time, and you get stuck in a regime, for example, then by changing the connection coefficients, you can get out of this regime. On the other hand, we often see after training that the connection coefficients are typically very large. And if they are large enough, then we get convergence towards a weighted supermodel. So the advantage of a weighted supermodel is that it's more synchronized than a connected supermodel, because you define a new state, as you can see in the figure here on the left, and you give that back to both models. So then we suffer the least possible from this variance reduction and smoothing. Yeah, I'm sorry, I have to sip a lot of water. I come from the rainiest city in Europe, and I'm still not used to the very dry air here. So I have a very dry throat and mouth all the time. I'm sorry. So that is an advantage of a weighted supermodel, that it's so synchronized. But that might not always be physically feasible, because you might pull the models too much out of their comfort zone. So then nudging, as you can see here in the figure on the right, with gradually bringing the models together, it's a softer approach. So then my PhD was about training of supermodels. So that means that we try to compute the optimal connections. So either the connection coefficient C in the connected supermodel, or the weights W in case of the weighted supermodel between the models. And then to train the supermodel, you need a lot of historical data or observations. And then previous training methods, they were based on the minimization of a cost function, but that's computationally very expensive. So my thesis objective was to develop and apply new efficient training schemes to train supermodels. I'm sorry. So then, how did I do this? Well, my first learning method, it's called cross-pollination in time, proposed by Lenny Smith originally. And the idea is that you combine different models by crossing their trajectories. And because you do that, you create a larger ensemble. So you can explore additional areas of your state space. And hopefully you can then get closer to the truth. So how does this work? Well, assume we have 3 different imperfect models, model 1, model 2, model 3. Then we start from one point in state space. And then we are going to integrate them until a point in time. And then, so we end up at 3 different points in time. And then from these 3 points, again, we are going to integrate all 3 models. So this is where this crossing of trajectories happens. So as you can see, you create this way a really large ensemble. It grows exponentially. So somehow you need to prune. And the way I chose to do this is, well, assume we have a truth, this black line over here in the right figure. Then every time step, we only continue with the model that is closest to the truth. So first model 3, then model 2, then model 1. And if we continue this for a certain amount of time steps, then you get an idea of how often each model has been chosen. So for example, here model 1 has been chosen 4 out of 20 time steps. And that means that we give model 1 a weight factor of 0.2. So just the frequency at which the individual model was found closest to the truth. So then I applied this method to the famous Lorenz 63 system. So I guess you're all familiar with this. You just have 3 equations for x, y, and z. And we have 3 parameter values, and the standard parameter values, they give rise to this butterfly shape. So then I created 2 imperfect models with different parameter values. And as you can see over here, they have really different behavior compared to the truth. So here my imperfect model 1, it reduces to 2 stable fixed points. And model 2, it has this butterfly shape, but there's clearly a bias in the z direction. So then after training of 200 time steps, then a weighted supermodel looks like this. So you have equations for x, y, and z. But because the parameters are linear in the equations, we can also get an immediate expression for the supermodel parameters, as you can see over here. And then when we calculate them, then we see that the supermodel parameters are actually really close to the truth. So then it's no surprise that after training, the supermodel attractor looks very similar to the true attractor. So then I also wanted to try another learning method, a synchronization-based learning method, the sync rule. So this was originally developed by Greg Dwayne in order to estimate parameters. And the difference between this rule and CPT is that with this rule, you update your weights during training. So you start with equal connections for both models, for example. And then during the training, you update your weights according to this rule, such that your supermodel will synchronize with the truth. And then this rule maybe looks a bit complicated, but it has an intuitive explanation of being the covariance between the error between the supermodel and the truth on one hand, and the tendency of the imperfect models on the other hand. So now I would like to show you some results with the SPEEDO model. SPEEDO is an intermediate complex global atmosphere ocean land model. And to give you an idea about the size, it has a spatial resolution at the equator of around 700 kilometers. So then during training, I have a perfect atmosphere and I create two imperfect atmospheres. And then this perfect atmosphere, it communicates its results to the ocean and the land model. And then the ocean and the land model, they communicate the results to the imperfect models. So this way you work with the perfect ocean and land model during training. But then after training, you only have your supermodel, you don't have the perfect atmosphere anymore. So then the supermodel looks like this. And then the ocean and the land model, they receive a weighted average of the fluxes of the imperfect atmospheres. So then I created different models by perturbing the parameter values. So I perturbed the relaxation timescale of convection, the relative humidity threshold, and the momentum diffusion timescale. And the reason I chose these parameters is because uncertainties in models are often within clouds and convection. So this might be the most realistic. So then I have parameter values for the truth, and I have two imperfect models with different parameter values. So in this experiment, I used the sync rule to train a connected supermodel. I have a training period of 1 year before the weights are stable. I use global connections. So that means that every equipment of the model gets the same connection coefficients. But I do have different connection coefficients for temperature and wind. And then during this experiment, I assume that every model time step, we have an observation available from the truth. So then the supermodel we created, it outperformed the individual models in, well, many aspects. But there's one result I would like to highlight, and that's the response to CO2 doubling. So when we double the amount of CO2 in the model, then in figure A, you can see the change in the perfect model. So this is the change in zonal winds at 850 hectopascal. So then, for example, you can see that here at the maritime continent, there's a weakening in the east-west component. And then panel B, C, and D, they show the error in this change. So then you can see that both imperfect models, they do not see this weakening of east-west component so strongly. They have a positive error. But then the supermodel, on the other hand, it doesn't have any error here at all. So I think this is a really nice example of reducing similar errors. So then I also wanted to try my CPT method to see if that also worked well in SPEEDO and to compare it with the sync rule. And I did this in the context of a weighted supermodel. But now I have the same model one as from before with the same parameter values. And I have 3 different imperfect models with basically the same perturbation in parameter values as before, but then distributed differently. So why would I do this? Well, Well, that's because of the convex hull principle. So this is a mathematical term, and it basically means that if your parameters appear linear in the equations, which they don't in this case, then there's a perfect linear combination with positive weights of the imperfect parameter values that is equal to the perfect parameter value. So it basically means, as you can see in this figure here on the right, that you kind of surround the truth with your imperfections. So for this experiment, I had again global weights. So every grid point gets the same weights. And I exchanged temperature, vorticity, and divergence between the models. So this is enough to have enough synchronization between the models. So then when we look at the results, I made a run for 40 years and calculated climatology. This is an example for temperature. And then we see the perfect model over here, this black line. And we see both supermodels, the CPT supermodel in pink, this line very close, and the supermodel trained by the sync rule in orange, also very close. So that's very good news, of course, because they're clearly better than the 4 imperfect models. But what I think is most interesting is that here all imperfect models, they overestimate the temperature. So that means that if you would just combine the models afterwards, as in a standard multi-model ensemble, and you would use positive weights, then you would always get something that is never better than the best imperfect model, which is still too warm. So I think that this shows that the convex hull approach can work really well. And that also an imperfect model that is maybe not so good as this imperfect model 1 still can contribute towards the supermodel if it has something that the other models don't have. But this convex hull approach does not always work. Sometimes models just cannot compensate for each other with positive weights. So then you might need negative weights. So here I have in this experiment the same model 1 from before. And now I have another model with parameter values that are all smaller than the parameter values of the truth. So in this experiment, I used the sync rule because with the sync rule, it's really easy to get negative weights. I didn't impose any constraints on the weights. You can get negative weights without any problem. For CPT, it's less straightforward because then you count how often you have used each model. So it's a bit difficult to count negatively. But I will come back to that. It's not impossible to get negative weights with CPT as well. So here, training with the sync rule, it results in stable weights, as you can see in the figure here on the right. Already after a week, they're quite stable. And they're also negative, or at least for vorticity and temperature. And then when we look at the results, so here I calculated the average error in wind at 200 hectopascal over 30 years. Then you see that both imperfect models, they have quite large errors. This one, imperfect model 6, even way more than model 1. But then the supermodel, on the other hand, well, it still clearly has some errors, but it's definitely an improvement compared to both imperfect models. And then also when we look at the short-term forecast quality, so here I calculated the difference between a perfect model trajectory and a trajectory with a slightly perturbed initial condition. So then also for the perfect model, at some point you get an error because of chaos. And then we see that, well, the supermodel clearly has an error much larger than that, but it's definitely an improvement compared to both imperfect models, these red lines over here. So our supermodel with negative weights, it performs better in short-term as well as long-term forecasts. So the experiments I showed you so far, I assumed that we have perfect observations always available. So unfortunately, that's not reality. In real applications, observations, they are noisy and sparse in time. So in order to work with that, we need a new definition of the weighted supermodel. Because we do not want to combine the models every time step anymore. Also because that's computationally very expensive. But also it's a bit difficult to train a supermodel that exchanges every time if your observations do not appear every time. So the solution is to combine the states instead of the tendencies with a certain frequency delta t. And we need to combine the states instead of the tendencies in order to still have a synchronization between the models. So then the supermodel looks like this. Don't get confused by this Kronecker delta. It just means that if we have a supermodel state, so here it's just the weighted superposition of the states of the imperfect models. Then if we have this, we give it back to the individual models to continue their run with. And if there is not a supermodel state, then individual models just continue with their run. So when we work with sparse and noisy observations, we also need some adaptation to the training methods, because it can be more difficult to follow observations during training. So for CPT, I worked with an iterative method. That means that we just perform the training as normal, and then we get a supermodel. And then the next iteration, we use this supermodel as another model you can choose from as being the closest model. So not only model 1 or model 2 is closest, but also the supermodel can be closest. And the idea of this is that hopefully the supermodel is already an improvement compared to the individual models. So hopefully it will then be easier to follow the observations. But if this is not enough, then we can also apply nudging towards the observations if the trajectory still diverges too much. And for CPT, I needed to add an extra term to the rule that made sure that the total update of the weights for the imperfect models equals 0. So for example, if your weights sum to 1 beforehand, then they will remain summed to 1. And that can be very important in order to maintain balances. So here I have an experiment with sparse and noisy observations. So I tried it both with CPT and the sync rule. I have the same setup as before. I have global weights for temperature, vorticity, and divergence. I have a model time step of 15 minutes. But now I work with sparse observations only every 24 hours. And the observations, I perturb them according to some Gaussian noise. And I have 3 different levels of perturbation. And for temperature, this corresponds to a standard deviation of 0.15 degrees, 0.75, and 1.5 degrees Celsius. So I did my experiment with the same imperfect models as from the very first SPEEDO experiment. And then in this figure here on the left, you can see the weights after training for the 3 different levels of perturbation. And then here, sorry, these lines over here, they indicate the weights that we get if we would have perfect observation experiments. And then you can see that also with these noise and sparsity observations, the weights are actually very close to the weights we get when we have perfect observations available all the time. So that's very encouraging. And this is an example of CPT, but we have similar results for the sync rule. So then the last thing I would like to show is that we can also get negative weights with CPT. So this is not straightforward because you're counting how often you use each model. But you can get around that by predefining a combination of the models. So you do not choose, in this case, whether model 1 or model 6 is closest to the truth, but you choose whether this combination minus model 1 plus 2 times model 6, or the other way around, 2 times model 1 minus model 6 is closest to the truth. And if you perform your training this way, then all of the weights will be between -1 and 2. So then you can actually get negative weights. And when I perform my training like this, then I get weights that are very close to the weights that I got with the sync rule. And I already knew from before that these weights were very good. So that's a good result, that also negative weights can work with CPT as well. So then to summarize, so I developed efficient algorithms to train supermodels, also in the context of sparse and noisy observations. I used them to train the globally coupled atmosphere ocean land model SPEEDO. The supermodels, they outperformed both the individual imperfect models as well as the multimodal ensemble approach. I defined which variables should be exchanged between the models in order to have a sufficient amount of synchronization. And I explored this possibility of having negative connections between the models as well. So then, of course, the question is whether we can make whether we can make the step towards training complex state-of-the-art models. So then one question is whether we can use the methods for training on longer timescales. Because so far the methods, you use them on very short timescales, both CPT and the sync rule, and that might not always be sufficient. So then to train on longer timescales, an idea might be to create a larger ensemble of trajectories during training, just to create more possibilities, a bit similar like the particle filter. And maybe that you do not only create a trajectory with the smallest RMSE compared to the observations, but also, for example, with respect to certain climatological features. So, for example, this double ITCC, we saw that you choose the model that does not have this double ITCC. So then the past couple of months, I explored the possibilities of a neural network. I think this can be promising, that you do not only have linear combinations between the models, as I had so far, but also non-linear combinations. But so far, I've not been very successful, I have to say. It might be a nice possibility. But then, of course, the big question is that so far I was using models that lived in the same phase space. But usually there is structural difference between the models. There's not only parametric error. So how do you proceed then? So the idea is to define a common state space, to apply the training methods over there, and then to use techniques from data assimilation to get these states back to the individual models. So there's still a lot of work to be done, but in principle, the training methods are ready to be applied to train the real state-of-the-art models. Thank you.
Thank you very much, Francine. A very comprehensive talk. Thank you so much. I want to welcome, we have a lot of people from the climate division. Hello to everyone. That's really wonderful to see, and from CU too. If you have a question, please raise your hand or just type it in the chat or indicate in the chat that you have a question, and I will call on you. While I'm waiting, I'm going to ask the first question. So I find this fascinating work, and obviously it has a lot of parallels to data assimilation. A lot of people in MCube do data assimilation. Everyone is familiar with the concept. They're nudging, obviously, and also now this very machine learning techniques, and it's sort of a form of learning. I'm always interested if you could use these interaction coefficient tendencies to actually find where the model error is coming from, to say, oh, it is in the parameter in the convection scheme, or the convection scheme is different. Can you, so I think you have shown that you can make a better forecast and you can have a better model with smaller biases, but can you learn where the bias came from?
Yeah, that's a good question. I've never really tried myself to do such a thing. I think it could be possible, but I also think we need to be a bit careful because you combine the models dynamically. You can get very different results than if you use them individually. So you create really a new model with new dynamical behavior. So I think you might not always be able to see where your error came from.
Thank you. There's a question by Anna.
Yeah, hi. Hi, Francine.
Hi.
Nice to see you.
Nice to see
Congratulations
you.
on your PhD. And I'm not an M-cubed and I'm not super familiar with data assimilation, so maybe this is a bit of a naive question. But so when you combine the atmospheric models, you at some point talked about not reducing the variance but still getting the model out of a regime. And I'm having a hard time sort of understanding exactly what happens, because the way that I can only think of this is sort of, one model says, I have very high wind speed here, and the other one says, no, I don't have high wind speed here. And then you actually do reduce some of that variance. So I must be misunderstanding something. Can you explain why your method doesn't reduce the variance, but then still can get better results, better dynamic results?
Yeah, so hopefully your models are synchronized enough that at some point in time, it will not be the case that one model says, oh, I have a very high wind speed, and the other one says, I have a very low wind speed. So hopefully they're already close together, and they follow together a trajectory influencing each other. So then you don't suffer from this variance reduction.
So maybe I'm having a timescale problem because you're looking at shorter timescales, then probably the dynamical behavior of the models stay closer together than if you integrate it over a long period of time. Is that correct?
Yeah. So I think ideally you would like to exchange information between the models as frequently as possible to maintain the synchronization in order that they do not completely diverge. So ideally, every time step, or for the atmosphere, for example, every 6 hours would be probably sufficient.
Okay, thank you.
You're welcome.
Peter has a question.
Francine, that was pretty interesting. I was curious, is there a optimum number of models that you could use, or is there a diminishing return? I mean, there must be some point where if you have 5 models, you don't improve it that much compared to, 2 models first, let's say.
It depends on your models, I think. So if you have a model that still can contribute something that the other models don't have, then it can still be beneficial. But of course, the more models you run, the more computationally expensive it gets. So I think, for example, 3 models, that's a good start point.
So there's real benefit, let's say just using 2 models, for instance, it's way better than just having just the individual one. There's a lot of benefit in that.
I hope so, yeah. So the way I see it is that it's always a layer on top. So you have your individual models. And of course, you want to have the best individual models as possible. But then by creating a supermodel, you can get something that's even better than those individual models.
Oh, okay, thanks.
Yeah, and if I could comment on this, how I understand it, in this Lorenz system, you can combine, let's say, 3 models with 3 dimensions. So you end up with a 9-dimensional model. So you're actually, the supermodel will have a higher dimensionality. And so that's what gives you the gain. But my guess would be if you have too many models, maybe the training will become more difficult too. So I think you have to find that sweet spot between having a high-dimensional model that you can capture these things you didn't capture before, but then not become too complex. And maybe, I don't know if the training becomes more difficult the more models you have too.
Yeah, also, I think the more coefficients, the more difficult it gets.
Chris Snyder has a question. Chris, please unmute yourself and ask it. If you can.
I can. Huh. You may hear kids in the background.
No problem.
I was wondering if you've tried experiments where the observations you're using to train have significant bias. That's a sort of a possibility of where you would contaminate the parameter estimates with this. You know, it's something that varies slowly in the same way that the parameter estimates will vary slowly.
Yeah, sorry, I'm not sure if I really got your question. But you mean, so for example...
Sorry, do you want me to explain?
Yeah, so for example, I have this experiment when I have 4 imperfect models that are all warmer than the truth. You mean that I have an experiment that's even stronger, that you have a larger difference between the imperfect models and the perfect model?
No, I'm talking about the experiments where you don't know the truth and you have observations that are imperfect. So instead of the observations having 0 mean error, they could have systematic, they could have a non-zero mean or even complicated functional dependence of the mean on things.
Yeah, so that's maybe you might need negative weights then, but hopefully you can get close to these observations as well.
Okay.
I don't see any questions right now. Maybe I ask a general question, and Francine, I don't expect you to answer this, but I'm wondering, so data assimilation is a special form now of supermodeling. I'm trying to understand better which way the Kalman filter is different from, you seem to use different norms to get the model and the observation of the truth together. Can you tell a bit more about the in which sense data assimilation, as we think about it with the Kalman filter, and supermodeling with the cost function and the 2 metrics you'd explained differ?
Sorry. Yes, I think the easiest with data assimilation, then, for example, with the Kalman filter, you add observations and then you adapt your trajectory. While with the supermodel, you have 2 phases. You have a training phase where you have data and then you train your weights. And hopefully you get optimal weights. And then you have your free run. So then you don't have any observations anymore. You just let the supermodel run. And hopefully, you will get a better prediction then.
That makes sense. Yeah, thank you. Question from Dan.
Thanks, Francine. I learned a lot. I have maybe like a basic naive question about the synchronization with these multiple models. I guess I'm wondering, like maybe in a somewhat pathological case where 2 models have very different attractors and you're trying to pull them back to a similar point and then run these forecasts, if I'm understanding correctly. I'm wondering how much of like the next of that forecast could be the model pulling itself back to where it wants to be.
Yeah, so indeed, models, of course, they want to go back to their own attractor as soon as possible. So you somehow need to find this balance. One model wants to go that direction, one model wants to go that direction. And then somehow the combination of these models needs to be perfect, that you end up in the middle where you want to be, not on one attractor and not on the other attractor. But yeah, I did not have problems with that so far. I can imagine, yeah, if you're not combining frequently enough, then you give the model a state that it doesn't feel comfortable with. And then you get this really rapid, yeah, you induce gravity waves and you mess things up maybe. So I think it's important to exchange between the models, yeah, as frequently as possible to avoid that to happen.
Thanks.
Thank you. There are more questions. I don't see any. So we're excited. You're starting your postdoc and continue to work with this. Maybe we welcome you back in a year or two for an update on the work you're doing. Thank you so much for your talk. And maybe we can all applaud and unmute or do a little applause. Thank you so much, Francine.
You're welcome. I'm very sorry for all the sipping and coughing. I hope I will get used to this climate soon.
We understand. We understand. And it's also, it's not just the dryness, it's also the altitude, right? So yeah.
Yeah, that's Thank you very much.
Thanks so much. Have a good afternoon, everyone.